Alright, so we have introduced the derivative as a function. We looked at it using the limit definition, how to find the derivative function. Looked at it graphically, and then we talked about the relationship between differentiability and continuity. So now we want to begin the process of finding the derivative function without having to go through every time the limit definition. So in our first video in this part, we looked at two examples, and finding limits involves a little bit of work algebraically. But we're now going to develop rules for differentiating functions. We are going to use the limit definition to develop these rules, but once we've used and see the rule, we won't need to redo that again. And so we start with the constant rule, and we've already developed this one, the derivative with respect to x. So remember this notation, d over dx. This says take the derivative with respect to x, and then in the parentheses or in the brackets is the function. And this is the function f of x equals c. So if f of x equals c, then we're saying f prime of x is equal to 0. And we proved this in the last lecture. The graph of f of x equals c is just a horizontal line, right? It's the constant function, horizontal line. The derivative anywhere is going to be 0, always. So the derivative is always 0. So for any constant, we say the derivative is equal to 0. Okay. I'm actually going to make a big jump, something we haven't looked at, and I'm going to look at the natural exponential function rule. Yeah, we're going to find the derivative of this guy right here. Actually, we're going to estimate it, and later on we'll be able to prove the derivative of the exponential function. But right now, I'm going to use the limit definition. So f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. All right, so here's our limit definition. So I'm going to use it to set this up. And f of x plus h is e to the x plus h, minus f of x is e to the x, all over h. Right. Now, if I plug in h equals 0, this is indeterminate, of course, but what I want to do is try and simplify this. What can I do to simplify? Well, I'll just have you note to recall something about the expression e to the x plus h. This is equal to e to the x times e to the h, because what do we do when we're multiplying like bases to different powers? What do we do with those exponents? We add them. Okay. And so do you see where we can go from this? Now I'll write it this way. What can we do now to simplify this expression? Well, up top I can factor out that e to the x. Okay, and then I want to talk about that. So let's factor out that e to the x. What is left? E to the h minus 1 all over h. Well, now x is certainly a variable, but look at our limit. What's changing? H is changing, right? We're changing h towards 0, right? We're getting closer and closer to 0, right? 0.1, sorry, it was 0.1, 0.01, 0.001, and so on, getting closer and closer to 0. And so h is changing, but x in terms of its relation to h is fixed. In other words, e to the x can be thought of as a constant with respect to h. And so I have a constant multiple times a function involving h. I can pull that constant out, right, which I'm going to do, right, and that's only because x is not changing in the limit process, and I can do that provided this limit here exists. Okay, so let's take a look at this limit. Here's the problem. I'm not going to be able to algebraically find this limit right now. Later on in the course we will be able to. Right now I can't, and so the way I'm going to find it is just numerically. I'm going to estimate it numerically. So I'm going to put this function in the calculator. So it's going to be e to the of course, h here, but in the calculator, yeah, we're just going to use x. So be careful, it's not, it's not this e to the x over here. So our x in the calculator is h. So e to the h minus 1, close parentheses for the top, divided by h, which again is x. Okay. And then I want to go to my table and see what's happening as x gets close to 0. So 0.5 is close to 0. I can get closer to 0, 0.1. I can get closer to 0, 0.01. I can get closer than that. And I can even get closer than that. And what do we appear to be approaching from the positive side of 0? Maybe 1, right? Getting closer and closer maybe to 1. Let's see from a below 0. So negative 0.5, negative 0.1, negative 0.01, negative 0.001, negative 0.0001. What do we appear to be approaching from the negative side of 0? Again, maybe 1. Okay, so it looks like 1 is my guess. Okay, it turns out this limit is exactly equal to 1. We did this numerically, but we will show later that is exactly equal to 1. But if this limit is 1, e to the x times 1 is e to the x. And so what are we doing? Let's go back to the beginning. The derivative of what function? E to the x. The derivative is what? E to the x. And so here's our rule for differentiating the natural exponential function. It's the easiest one to find. The derivative of e to the x is e to the x. That's the natural exponential function rule. Okay? And that tells me that the slope at any point on e to the x is equal to the value of the function at that point. So at x equal 2, what's the slope? E squared. At x equals 0, what is it? E to the 0, or 1, and so on. And that's good if you think about the exponential function, right? The graph looks like this. At 0, it's equal to 1, it looks like this, right? Clearly, if you think about this function, this tangent line, right, at any point, if I pick the tangent line at any point, it's going to be positive, right? Which is good because the derivative is always positive, right? E to the x is always greater than 0 for any value of x. And as x gets bigger, e to the x gets bigger, right? And so the slope is indeed doing that as we move from left to right. The slope of the line, the steepness of the line getting more positive, right? The slope is getting more positive as we move left to right. Okay, that's an easy rule to remember. So we just do that right off the bat so that we can make use of that rule. Okay. The next rule I want to talk about is the power rule. Okay, so this is not a power rule because the variable is in the exponent. Okay, if the variable is the base, like if I have x squared or x cubed, we're going to learn how to find the derivative of those type functions. Okay, so I'm going to first prove it where we're looking at the function x to the n, where n is any positive integer greater than 1. Okay. If n is 1, what's the derivative of f of x equals x? F of x equals x, that's a linear function, right? It has a slope of 1. The derivative of f of x equals x is 1 because the slope of that line. But if it's x squared, which is the parabola, or x cubed, or so on, x to the 4th and higher, what's the derivative at any point x, right? It's not the same, it changes. Okay. In order to do this, we're going to need something called the binomial theorem. So I don't know how many of you know how to expand binomials. X plus h to the first is just x plus h. X plus h squared, I hope everyone knows, is x squared plus 2xh plus h squared. What about x plus h cubed? Can you do that real quick? Well, here it is. Right? If I multiply this thing by the quantity x plus h, I've got to distribute, right? Multiply everything by x, multiply by everything by h, combine like terms, and when you do that, you're going to get this. X plus h to the 4th is this. X plus h to the 5th is this. Notice the pattern. First of all, there's 2 terms when I do to the first power, obviously. 3 terms for x plus h squared. X plus h cubed is 4 terms. So whatever the power is, there's 1 more term. And the first term, I think you can guess what it is, right? X squared, x cubed, x to the 4th, x to the 5th. What's it going to be down here? When I do x plus h to the 6th, It's going to be x to the 6th. All right? And then what's the last term? H squared, h cubed, h to the 4th, h to the 5th, h to the 6th, and so on, right? What about the terms in between, though? Well, there, without looking at the numerical coefficient, look at the patterns of x, right? This is x to the 5th, then what? X to the 4th, then what? X cubed, then what? X squared, then what? X, and then what? X to the 0, which is 1, there's no x, right? It goes down by 1, right? The power of x goes down by 1 each time. What about the power of h? Well, it's h to the 0 or 1, h to the 1st, h squared, h cubed, h to the 4th. You see how that works? So you understand, I think, the variable portion. The question is, how do we get these numbers 5, 10, 10, 5, or 4, 6, 4, and so on? How do we get those? Well, if I make a pattern where I just take the coefficients in front of all the terms, 1x plus 1h, 1x squared, 2xh, 1h squared, 1, 2, 1, 1, 3, 3, 1, right, that line, 1, 4, 6, 4, 1, that line, 1, 5, 10, 10, 5, 1, that line. Some of you may have seen this. This is known as Pascal's triangle. If you've seen it, then maybe you know how to get the next set of numbers, which will help me out to be able to expand x plus h to the 6th power. Okay? Let me give you a hint if you don't know. Obviously, we see 1, 1, 1, 1, 1, 1, 1, so the next is going to be 1. Here we see 1, 1, 1, 1, 1, 1, 1, so the last is going to be 1. And so what goes in between, how do I determine that? Well, let me help you out. Going from this row, which was x plus h to the 4th coefficients, to the next row, x plus h to the 5th coefficients, to get this 5, I'm going to show you how you do that with arrows. And to get this 10. And to get this 10. And to get this 5. How am I doing it? What am I doing? I'm adding the coefficients above to get the one in the middle. So 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Look here. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. See how that's working? So now we can do this. What's 1 plus 5? 6. 5 plus 10, 15. 10 plus 10, 20. 20 plus 5, 15. 5 plus 1, 6. So of course there's some symmetry to these patterns, but now we know how to write x plus h to the 6th power, right? It's going to be what? 1x to the 6th plus 6x to the 5th h. All right, so I can come up here. X plus h to the 6th is going to be 1x to the 6th plus what? 6x to the 5th h plus what? 15. And what do I do? X to the 4th, h goes up, h squared, plus what? 20, x cubed, h cubed, plus what? 15, x squared, h to the 4th, plus 6, x, h to the 5th, plus 1, what? H to the 6th. Right? And you can do x plus h to the 7th now, just real quick. So the binomial theorem is pretty powerful. Okay? Now, obviously, we want to do x plus h to the 50th power. You've got to go a long way down. There is a way to find the formula for the binomial coefficients without going through 50 levels of the Pascal's triangle, which would be tedious. And you can see your algebra review sheet in front of the book for that. Really, we don't need all that, the formula for all this. This may be interesting if you've never seen this. But I want to use this idea to find the derivative of x to the n. So let's do that. If f of x is equal to x to the n, where n is any integer, again, 2 or more, then f prime of x is, let's write out the definition, limit as h goes to 0, f of x plus h minus f of x over h. All right? So what is f of x plus h? I replace x with x plus h. I get x plus h to the n power. Minus f of x, that is just x to the n power, all over h. Now again, if I plug in h equals 0, I'm going to get 0 over 0. It's indeterminate. But what I want to do now is I want to expand x plus h to the nth power. Okay? So we were doing x plus h expansions here. This time it's to the nth power. So how do we do that? Well, what do we know? X plus h to the first, we start with an x. X plus h squared, we start with x squared. To the third, x cubed. To the fourth, x to the fourth. To the fifth, x to the fifth. To the sixth, x to the sixth. So if it's to the nth, what's the first term going to be? X to the nth. Right? Well, let's look at the next term. Look at the pattern here. The next term, well, that's an h. Here's 2x h, 3x squared, 4x cubed, 5x to the fourth, 6. Look at that coefficient pattern. 1, 2, 3, 4, 5, 6. Right? So if it's 2, it's 2. 3, it's 3. 4, it's 4. 5, it's 5. 6, it's 6. So if it's n, that coefficient is n. And what is it? X to what? We subtract 1 from the power, n minus 1, and then we have to add the h. Right? That's the second term. Now the next term, I don't know about the coefficient. I'm just going to say it's some number. I don't know. So it'll be in terms of n. There's actually a formula I can write. What's the value of x, though? It's what? X to the n. 1 less is n minus 1. 1 more less is what? N minus 2. H goes up by 1. No h's. H to the first. H to the second. Right? And so on. That continues all the way down to the last one, which is just going to be what? H to the n would be our last one, right? H to the n, right? H squared, h cubed, h fourth, h fifth, h sixth, h to the n. So there's a bunch of terms in here that dot 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 means there's a bunch that we're excluding, but we really don't need them, as you'll see here in a moment. That is f of x plus h. That's x plus h to the nth power expanded out, minus x to the n. All this over our lonely little h down here. Now, simplify. X to the n minus x to the n. Well, that's gone. That's 0. So what's left up top? X to the n minus x to the n is gone. I've got this n x to the n minus 1 h plus some number x to the n minus 2 h squared plus dot 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 all the way h to the n all over h. So I've subtracted x to the n minus x to the n, that's 0. Now, again, if I plug in h equals 0, every term has an h in it, so that's all going to be 0 up top, 0 on the bottom. We're indeterminate. However, I just said every term has an h. What can I do? I can factor out that h. Right? Factor out the h here. What am I left with? Just n x to the n minus 1. Factor the h here. What do I have? Some number, again, I don't know what number this is, some number, x to the n minus 2. If I pull out h from h squared, what's that leave me? 1h, right? And each of these terms is going to have an h. I'm going to pull it out. Until the last term, I'm going to pull out 1h from h to the n. That leaves me h to the n minus 1. Okay. Now what? This h in the numerator and this h in the denominator, they form a ratio of 1, right? H divided by h is 1. And what am I left with? The limit as h goes to 0 of just what's in the parentheses. Well, can I plug in h equals 0? Is it continuous? Yeah. And what's going to happen to all these terms? Every term here has an h. This has an h. These dot dot dot, a bunch of terms, but each one has an h, right? The next one will have h squared, h cubed, all the way to h to the n minus 1. All these terms, what happens to them as h goes to 0? They all go to 0. This is just equal to then n times x to the n minus 1, because all these have an h in them, and all of them go to 0. Okay? And there is our shortcut rule. We've proved that the derivative of x to the n is n times x to the n minus 1. And this is called the power rule. This is called the power rule. It only works when the base is the variable and the the exponent is a constant. In fact, we proved this true for n being an integer greater than 1, but it turns out that this is true for any real number n. Now I haven't proved that, but we're going to use that. Okay, so we've proved it only for integers greater than or equal to 2, but here it is actually true for any real number, positive, negative, whatever. Okay. In fact, if x is 1, x to the first power is just x, what's the derivative of x? We know it's 1, right? Derivative of x, f of x equals x is a line of slope 1. What's the derivative of x by this formula? The 1, bring the 1 down, x to the 1 minus 1 is 0. We'll say x to the 0 is what? 1. So I get 1, right? This formula works even for the case when n is 1. Okay. Well, let's take a look at this rule then in some examples. Okay. Find the derivative of the following functions. Y is equal to x to the 12. Well, n is 12, so how do I do this? Basically, the idea is sort of bring the n down in front and subtract 1 from the exponent. So if I want to find the derivative of y with respect to x, or I can write this again, the derivative with respect to x of y, or again I can write this as y prime, again just reminding you of the different notations, is what? Bring the 12 down, x subtract 1 from 12, I get 11. And there it is. If you try to do the limit definition on this, you'd have to expand x plus h to the 12th power. Think about how long that's going to be. X plus h to the 6th is all this. You're going to have 13 terms, right? Combined like terms. You've got to do all this work, but we know what we're going to get by the shortcut formula, if you will. We know this is the shortcut. This is always going to be what we get. So we are saving ourselves a whole bunch of time, which I hope is making you happy at this point. Here, what's g prime of t? What's the derivative by the rule? Well, here the exponent is 2.5. So the 2.5 comes down, t to the 1.5. I'll leave it as decimal since that's the way we were given the original problem. There it is. End story. And that would have been hard to do. You know, expanding t plus h to the 2.5 power is difficult. Right? That's going to involve it's really 2.5 to the 5/2 power. What about this? Wait, you said this is not a power rule. It's not x to some power. It's the square root of x. Well, it actually is, because the square root of x is x to what power? 1/2 power. Remember, x to the 1/2 is the square root. So I can find the derivative of s with respect to x by the power rule. Bring the 1/2 down, 1/2 x, and subtract 1 from 1/2. Now be careful. 1/2 minus 1 is negative 1/2. And so let's simplify this then. I don't want to write this with a negative exponent. This is 1/2 times 1 over x to the 1/2. X to the 1/2 is the square root of x, so I can write this as 1 over 2 times the square root of x. And there's my derivative. Again, saving me lots of time with this newfound power rule for derivatives. So otherwise I'd have to push this through the limit definition, and I have to use conjugate to simplify, and so on and so forth. And what about this? Can I just say the derivative is 1 over 4x cubed? Bring the 4 down? No, because this is not x to the 4th. This is 1 over x to the 4th. This is really x to what power? X to the negative 4th. So be careful. We don't have any rule where I can just say if I have a quotient, I just take the derivative of the top and the derivative of the bottom or something like that. We'll talk about the quotient rule next in the next set of videos. So what is the derivative of this function? The exponent is negative 4. Bring that down. And then I subtract 1 from negative 4. Be careful. Negative 4 minus 1 is negative 5, not negative 3. So this becomes negative 4 times 1 over x to the 5th, which is negative 4 over x to the 5th. Do one more. Is this a power rule? Well, yeah, I just have to rewrite it a little bit. This is 1 over what? The cube root of u to the 5th is what? U to what power? The cube root of u to the 5th is u to the 5/3 power. And then if I rewrite this, what, u to the negative 5/3 power, that's what I want it to be in. That's the form it has to be in. Okay, so the derivative d prime will just say, notice d is the dependent variable, u is the independent variable. U to the n is negative 5/3, so bring that negative 5/3 down. Subtract 1 from negative 5/3. So subtracting 1 is subtracting 3/3. Negative 5 minus 3 is negative 8/3. So this is negative 5/3 times 1 over u to the positive 8/3. And so I get negative 5 over 3u to the 8/3. And typically, right, I would want the answer to be written, since it was given without negative exponents, you shouldn't leave it in this form. You should rewrite it without negative exponents. So that is several examples involving the power rule. Okay, we're going to stop this video. We're going to do one more video after this one. It's going to be a short one, and we're going to basically show how we can find the derivative of any polynomial function, and then we'll finish out this section with that.